Hi, this presentation provides an overview of the rapidly expanding literature on music and memory between 2020 and 2025 and situates its key interdisciplinary trends while introducing the structural challenges that continue to shape research across health sciences and music-related disciplines. Through this presentation, I will first outline the research background, then identify the central problems in the field, and finally present a software system as a state-of-the-art proposal addressing these challenges. Between 2020 and 2025, research on music and memory expanded rapidly across health sciences and music-related disciplines as reflected in publications indexed under key terms such as music and memory, music and dementia, and Alzheimer's disease. During this period, studies in health sciences increasingly examined music as a cognitive and therapeutic stimulus, focusing on memory recall, emotional engagement, and quality of life in clinical and aging populations. At the same time, music scholarship explored memory through musical perception, structure, performance, and cultural context, emphasizing harmony, melody, and form as cognitively meaningful dimensions. This body of recent literature situates music as a temporally structured auditory phenomenon capable of engaging cognitive, emotional, and neural processes simultaneously, providing a rich interdisciplinary foundation for investigating memory in music-related research contexts. In terms of the problems in the field, this study shows four main areas. First, health sciences research on music and memory predominantly treats music as a uniform stimulus, with nearly all studies excluding harmonic, melodic, or formal structural analysis. This limits the capacity to relate cognitive or behavioral outcomes to musically meaningful units. Secondly, all music domain studies retain analytical depth. They remain largely isolated from real-time clinical, behavioral, and neurophysiological research contexts. As a result, structural music knowledge rarely informs applied or therapeutic studies. Existing studies typically rely on offline analysis and post-hoc synchronization, preventing precise temporal alignment between musical events and physiological or behavioral data. This weakens causal interpretation in music memory research. Finally, current automatic music analysis and Roman numeral analysis systems rely heavily on manually annotated expert datasets. This dependence constrains scalability, automation, and integration into real-time interdisciplinary research environments. As a state-of-the-art proposal to address these problems, the present work introduces a real-time music software system that automatically models musical structure, performs precise Roman numeral analysis in real time for the first time within computational music theory research, and synchronizes this information with behavioral and physiological data, thereby enabling integrated multimodal corpus creation for interdisciplinary research. In the following part of this presentation, I will introduce the main functionalities of the software and conclude with a brief demonstration of its capabilities. First, I open the program folder and start the external sources that feed data into our system. I launch Ableton Live, which records MIDI data from musical performances in real time. Then I activate Anaconda, which runs the Python code that processes our signals. Finally, I open Visual Studio Code from same environment to oversee the Python and JavaScript components working together. Now I need to start two servers that act as bridges between our data sources and the display interface. The first server, server.cjs, manages the MIDI data stream from Ableton Live. It captures incoming musical information like notes, timing, and velocity, then broadcasts this data through WebSocket connections so our visualization interface can display the musical performance in real time alongside the brain signals. The second server OpenBCI simulator.cjs, creates simulated brain data for testing purposes. This simulator produces the same 8-channel EEG signals at 250 samples per second that we would get from real hardware, allowing us to develop and test without needing the physical device connected. With both servers running, I execute the Python script that collects data streams from both sources. The system synchronizes the brain signals with the musical performance data and displays everything on the user interface. The user interface is structured as a modular multimodal environment that supports the synchronized analysis of behavior, music, and electrophysiology. At the upper level, 3 horizontally aligned panels define the system's core functions. The left panel constitutes the behavioral domain, providing live video monitoring and interaction controls for participant-related processes. The central panel governs musical settings and structural parameters, functioning as the temporal and analytical core of the system. In contrast, the right panel is dedicated to electrophysiological processes, enabling real-time monitoring and configuration of neural signals. Below these primary panels, 4 supplementary sections are arranged vertically. These include participant demographics, extended musical settings, behavioral supplements, and a final data processing layer that visualizes synchronization and internal computational workflows across modalities. This system uses phaseAPI.js to identify 7 emotions: happiness, sadness, anger, fear, disgust, surprise, and neutral during musical performances. The browser-based analysis quantifies emotional intensity from 0 to 100 in real time, correlating facial responses with performance data. To activate this analytical function, I first establish the temporal parameters by inputting a tempo value, in this demonstration 60 bits per minute. Subsequently, I initiate playback of the MIDI file to commence data collection. Upon accessing the data visualization panel located on the left side of the interface, we observe the photographic captures the system acquires at each quantization interval, specifically at 16 note divisions corresponding to the currently specified tempo. Adjacent to each photograph, the system displays the computed facial expression values, providing a time-synchronized record of effective responses aligned with the musical performance timeline. This section presents the go-no-go test, a paradigm assessing attention response inhibition and decision-making by examining how attentional control unfolds over time in response to musical stimulus markers. In the present task, the musical tempo is fixed at 60 BPM again. Task is designed as a simple attention task based on harmonic change detection. As music plays, I press and hold a button whenever a chord change occurs in the music. At the exact moment of this behavioral response, a go marker appears on the recorded signal. In this way, perceptual detection of musical structure and motor action are explicitly synchronized with the same temporal framework. Then, I marked all later chord changes in the same manner, allowing sustained attention and consistency of responses to be examined through the task. In this final stage, all marked go events are displayed in a tabular format, making explicit the temporal correspondence between chord changes, behavioral responses, and the underlying signal data. This section outlines valence analysis through 2 dimensions, external and internal. External valence refers to objective evaluations of a sound's character, whereas internal valence captures the listener's personal emotional interpretation, which may differ significantly. While listening to the music, I label each evaluative moment through manual input. After pressing the pointer button, activating the positive marker generates a green line on the signal, indicating a positive valence judgment. This marking persists until the pointer is pressed again, at which point it ends and remains inactive until the next judgment. When we examine the corresponding column in the table, positive judgments appear as 1, negative judgments as -1, and neutral responses as 0. This column represents the externally defined evaluative category, indicating how the sound is classified, positive, negative, or neutral, regardless of the listener's individual subjective interpretation. For the internal mode of valence analysis, the procedure remains identical. However, the resulting judgments are recorded in dedicated columns specific to internal valence within the table. Emotion analysis, a supplementary component of the behavioral panel, presents 26 emotional texts from positive to negative, providing a finer-grained extension of valence analysis with identical interaction methods. At this stage, external judgments of emotional attributes were measured. Subsequently, the same assessment is conducted using the internal evaluation mode. In this section, I outline the analysis workflow: functional harmony via Roman numerals, voice isolation through root, bass, and soprano, and temporal structuring with meter, quantization, beat, and bar. Together, these layers produce precise data entries for real-time multimodal research. These 12 white boxes indicate how many pitch classes are present within a temporal buffer. Depending on the count, the corresponding box illuminates green. For instance, one pitch class activates the first box, whereas 4 pitch classes activate the fourth, and so on. The program integrates real-time audio signal processing with incoming MIDI data. When the Start FFT button is activated, the left panel becomes active and displays a frequency spectrum divided into 256 discrete pins. Users can then select the desired audio input device from available system options, ensuring compatibility with different hardware configurations. Although alternative buffer sizes can be chosen instead of the default 256 pins, all spectral analysis and visualizations are computed according to the selected setting. Musical parameters are set in the supplementary section, where the time signature and dynamic memory are automatically assigned according to harmonic completeness within the buffer. Composition start and stop markers define the boundaries of the analyzed MIDI file, sending corresponding beginning and ending time messages to the digital audio workstation, namely Ableton Live. Finally, the key and key quality of the composition are assigned. For the present MIDI file in C major, the inputs are set to 0 for the key and capital M for the key quality. As the MIDI file plays, the system displays Roman numerals alongside root, bass, and soprano voices. In parallel, metrical information, time signature, quantization, beat, and bar is shown. For each bar, white boxes indicate how many notes occur within that segment. Then, each data point is assigned to its corresponding column in the table. I now focus on the EEG component of the program. The left panel displays band power measures from 8 EEG channels computed with tempo and time signature locked windows defined by 3 inputs: milliseconds, beat, and bar. If both bar and beat values are 0, the EEG sample calculation window uses the millisecond or quantization value to define each window and computes average power across all frequency bands for every EEG channel. If only the bar value is 0, the system relies on the beat value. However, when both bar and beat inputs contain values, EEG samples are computed according to temporal duration specified by the bar input. In the center of the panel, to ensure accurate observation, the system computes the expected number of EEG samples based on the sampling rate, 250 Hz in this case, and compares this value with the samples received from the OpenBCI hardware. When the discrepancy between expected and actual counts remains sufficiently small, the resulting measurements are considered reliable. In this case, the bar value is set to 1, so EEG samples are collected across each musical bar. With a tempo of 60 BPM and a 4/4 time signature, one bar lasts 4 seconds and the system outputs the average band power values for all 8 EEG channels. In this section, I demonstrate the full functionality of the program. First, EEG windows are set to 1 bar. With a tempo of 60 BPM and a 4/4 time signature, EEG samples are calculated every 4 seconds and summarized accordingly. Next, the start and end points of the MIDI file are defined, beginning at the first beat of the second bar and ending at the first beat of the 10th bar. The key is then specified as C major, followed by activation of the audio analysis module. At this stage, the program is ready to collect physiological and behavioral data. Finally, behavioral test options are selected, and all resulting data are displayed in the program table and exported as an Excel file. In conclusion, this presentation has outlined the rapid growth of music and memory research, identified key interdisciplinary gaps, and introduced a real-time software system designed to address these challenges. By integrating automatic structural modeling, real-time music theoretically appropriate Roman numeral analysis, and synchronized multimodal data collection, the system bridges music theory, clinical research, and computational analysis. Together, these capabilities offer a scalable foundation for future interdisciplinary studies and open new pathways for understanding how musical structure interacts with memory-related processes.